with Team 36. Today we are going to introduce you to our capstone project. We'll start with a poster presentation. In the upcoming slides, we will go through each of the sections on this poster. Millimeter wave is a radar technology that transmits signal with wavelengths in the millimeter range. Due to its use of small wavelengths, it can theoretically detect movements on the order of millimeters and distinguish two objects that are only 4 cm apart. This type of radar is primarily used on vehicles, but we want to explore its capability on detecting and identifying hand gestures. Gesture-based controlling allows users to give instructions to the computer without directly contacting a control panel. This is useful when users cannot touch the control panel due to wet or dirty hands. It could also be helpful for visually impaired people and media multitaskers like drivers and gamers, because they don't have to look at the control panel to give specific instructions. Currently, there is no well-established radar-based gesture recognition module in the market yet, but radar does offer some unique advantages over the more popular image-based gesture recognition. For example, radar can operate regardless of lighting conditions. Radar signals can penetrate certain materials, so the system can potentially be embedded in other systems. Radar infringes less privacy issues as radar data doesn't reveal as much personal information as images. And last but not least, radar data is generally smaller in size than image data, which helps save memory and computational complexity of the recognition model. Now here's an overview of the radar-based gesture recognition system we have implemented. We are using a millimeter wave radar development board from Texas Instruments called AWR1443. Its antenna configuration allows it to detect movements along all 3 axes. This is significant because, as we mentioned before, the primary use of this type of radar is for vehicles. It is not designed to detect vertical movements, but the ability of AWR1443 to detect vertical movements makes it possible to identify a larger variety of gestures. We implemented a pre-processing block that collects, decodes, and parses raw data from the radar board into desired format. Then the data is passed into a machine learning model to identify gestures. Our model uses the LSTM network, which is a type of recurrent neural network that is good at identifying wave patterns. The identified gestures are then sent to 2 applications that we have developed to showcase sample use cases of a gesture recognition system. One is a map application that lets users manipulate the view of map with gestures, for example, swiping left or zooming in. The other is a narrative game that we have designed that lets users solve puzzles and progress through a story with gestures. There is one more specification that I haven't covered. We have defined the detection area for our system to be a quarter sphere with radius 0.5 meter in front of the radar antenna. The pre-processing block will filter out any stationary objects or objects outside of the detection area to minimize noises passing to the recognition model. The pre-processing block sends 10 frames of data per second. Each frame includes the XYZ coordinates of all moving objects detected and the velocity at which they are moving.
Now let's see some verification tests for our system. First, the system only responds to movements inside detection area. And for the machine learning module, we achieve over 90% accuracy for each gestures, as shown in the table. There will be a live demo on each of those gestures be shown after. We also measure the latency of each module. We want our module to have a latency of less than 33 milliseconds, equivalently 30 frames per second. The reason why we choose 30 frames per second is that it's usually used for live TV shows or video streams, and people will not feel laggy with 30 frames per second. the machine learning model and the narrative game communicate with other modules in memory, so their performance reaches the requirement. However, the map application requires an I/O operation to get data from the machine learning model, which is much more time-consuming and causes it to fail the test.
Hi, this is Siyuan. I'm covering the demo section of our design. I will first start with explaining the demo setups, what will happen during the demo video, and then I will play the video. Most of the motions are tested in pairs for simplicity. This demo is about the push motion and the pull motion our system can detect. The push and pull motion are defined as moving away and towards the radar. You may see some failed detections of a pull detected as rotations. This matches the confusion matrix of our machine learning module. The second demo is about the left motion and the right motion. In general, as you see near the end of the demo, the accuracy reduces if the duration of the motion or the distance of the user hand travels is shorter than expected. This video is about the up and down motions. These motions are defined along the z-axis. As you will see in the demo, up and down in general have lower accuracy as the radar has a lower z-axis resolutions. Also, the module may confuse between up and down, which match our data analysis result that up and down are in general have similar data patterns. This one is about the rotation. Our system supports both the clockwise rotation and the counterclockwise rotation. As you will see in the video, the rotations are started from the lower end and draw a whole circle. The model may bias towards a down motion if the circle is drawn lower, or up motion if it is higher than expected. The final one is a special gesture we support. It defined within the near range of the radar. We see that the accuracy of the motion is pretty good, but the number of generated data points may not be large enough for the machine learning module to predict the result. This is because of the duration of the motion is relatively shorter. This motion also needs to be right in front of the antenna on board to ensure a good accuracy. The following sections are the application demos. There are two applications proposed, a video game and a map. The first application demo is one thing of the video game. In the story, you are required to cut down some wood. You will need to first do a push to put the wood there and use up and down motion to cut it. There is also a surprise after that. This is the following part of the story, where you need to get the password of the bomb. Notice that this time the combination of gestures is complex, and you may also see that our system has a weakness to handle the transition between the gestures naturally. The next application is our map. You will see how the hand gesture can be used to control the map. Where rotation is for zoom in and out, the x-axis motion is used for left and right, and the y-axis motions are used for up and down. In the next session, I will continue with my key contributions. For the beginning portion of the project, I was in charge of hardware aspects, including turning the configuration setting of the radar, understanding the provided hardware, and extract data from it. After the data is well formatted and understood, I move on to design an alternative machinery module using the time series definition. This is the module that we are using in our final design, as it is proving to be better than the original one.
I'm mainly responsible for developing the map application. The map application uses a JavaScript graphics library called Mapbox to render interactive maps. I implemented the protocol to transfer identified gestures from the recognition model to the map via UDP socket. Then I use the received gesture type to update the view of the map. I also designed a feature that allows users to select the style of map on the menu page by moving their hand around, much like moving a virtual mouse. The moving dot on the page is their cursor. When they land on the desired option, they can do the sum up gesture to click that option. and then the style of the map will be changed. This feature is not shown in the demo because it requires our model to correctly identify the sum-up gesture anywhere within the detection area, which hasn't achieved desired accuracy.
I'm in charge of developing this narrative game application based on Pygame, and also I've created all the demo projects for all of our milestones, including the snake games in our first demo to our supervisors and the simulation of Google Solid Watch in our R presentation. Also, I'm responsible for creating this video, and along the way, I've developed several radar data visualization tools to help the build and the testing of our machine learning model.
In the early stage of this project, I focused on building machine learning model for 2D radar, during which I collected 10,000 data and used 3D convolutional neural network, which can interpret data signal as video. The model finally achieved 95% accuracy on 6 gestures, but 50% accuracy on 9 gestures because of missing the z-axis. After we abandoned 2D radar and switched to 3D radar, I focused on learning the property of data and model. I performed the principal component analysis to learn the separability of dataset. For example, in the graph, we can see that the push and pull can be easily separated. I also perform attention analysis of the model. Attention analysis is a test for what level of noise will make the model change its decision. And from this analysis, I learned that our model is very sensitive to small noises, stretch, and shrink. With that knowledge, I performed data augmentation properly. This increased our machine learning model's accuracy from 94.4 to 95.4. During the design of the system, we encountered and bypassed several challenges. I will explain the challenges related to collector module and the analyzer module. First, when we choose hand gestures, we find it is hard to design gestures that is not only identifiable by machine learning model, but also useful and meaningful to the application. The way we use to design better gestures is to first plot and understand the waveform of the radar signal. For example, swiping left and right will cause the x-axis of the signal to change rapidly, while swipe up and down will cause the Z signal to change rapidly. We also use a technique named principal component analysis to project a radar signal from a high-dimensional space to a 2D space, so that we, as human beings, can visualize and understand how distinguishable each type of data is. Second, because this project is a research-based project, there's no existing database for radar hand gesture signal. We have to collect data samples from scratches. Usually, a machine learning model needs millions of samples to achieve good result. However, we only collect 10,000 2D radar samples and 3,000 3D radar samples. And the coronavirus situation also makes it difficult to collect samples from different people. So to get more data, we use a technique called data augmentation, during which we randomly add small noises and doing small stretches and shrinks to the data set we already have. This technique virtually increase the data set and make our model more robust to noises. Third, during the analysis of the 2D radar signal, we found that some important gestures are not distinguishable. For example, swiping up and down, which eventually forces us to use 3D radar. After switching to 3D radar, we are able to identify gestures that involve the motion on z-axis. As I mentioned, swipe up and down, and in addition, circle clockwise and circle counterclockwise.
Thank you, Jinkai, for covering challenges on the collector and analyzer side. I will cover some of the challenges that we face on the application side. The first challenge is that our map application experiences heavy delay when using WebSocket in communication between analyzer module and application module. Since two modules are written in two different programming languages, it is hard for analyzer to receive data from collector module and, in the meantime, maintaining the socket communication. Our team finds the delay is minimal when changing the WebSocket to the UDP socket. This decreases the delay, however, the delay is still noticeable. The second challenge is that during experimentation, we found that it is hard for our system to detect two gestures simultaneously. And our originally proposed card game requires exactly that. Imagine a card game that you can turn while accelerating. So we changed the card game to a narrative game application that restricts the user to perform only one instruction at a time. Users only unlock the next instruction upon finishing the current one. It turns out this helps the detection of the gesture and it makes it easier for the collector module. But before we move on to the future plan, I want to walk you through some of the challenges that remain unsolved. The first challenge is that our machine learning model has tendency to detect Siyuan's hand better, because a big portion of the samples are collected by him. Adding to that, those gesture samples are collected in his room and the analyzer remembers his way of doing the gestures, so inevitably results in some bias in terms of location, where gestures are performed, or the way gestures are performed. Also, we have challenges detecting the transition of two gestures because we found it easy to determine the start of the motion, while we found no good way to define the end of the motion. Bearing those three unsolved challenges in mind, we come up with our future plan. First thing we want to do in the future is to acquire a radar with better detection performance on the z-axis, because almost all the more advanced gestures like the thumb up and the zoom in zoom out one requires high accuracy on detecting movement on the z-axis. Second thing we can do is to improve our analyzer model by adding noise on the end of the samples. Right now we collect 16 frames of samples for one gesture, and our analyzer tends to focus on the first few frames of the samples. Adding noise is able to shift some of the focus to the end of the samples to achieve higher overall detection accuracy. Third thing is to collect more gestures in different places from different people. With large enough sample size, we believe we can overcome the bias problem we had in our current model. And last but not least, we can improve user experience for our application in different ways. We can design some mechanism to direct the user to the location with maximum detection efficiency before the application begins, such as providing visual guidance or through voice. Also adding voice notification for visually challenged people so that they can better utilize our system. And also we can integrate our whole system into a programming library and share it online. Thank you. That's the end of our video.